Thanks a lot, Alessia, for the introduction. Thanks also to the organizers for the invitation. I'm very happy to be given the opportunity to give this talk. Okay, sadly, I could not come to Strasbourg, but I hope that still we can have some discussions after my talk. So you might not know me because I'm not familiar with the OPODIS conference nor the distributed computing community. So as Alessia said, I work in the formal methods community and more specifically in the model checking community. But recently I got interested in what model checking can bring to the distributed computing community. So today I'd like to talk about this experience of again, what model checking can bring to distributed algorithms. So this talk will be based on joint work with several people: Igor Konov, Mariana Lazic, Bastian Thomas, and Josef Wieder. And you might, I think you might know Josef, who is a contributor also in distributed computing. So I just wanted to say that I don't have any feedback on the audience, or so feel free to interrupt if you have a question during the talk. Even if I don't see you, feel free to interrupt. Okay, so let's start. So since you might not be familiar with model checking, I wanted to start with an introduction to what model checking is. So the main question model checking addresses is, given a system and a requirement, whether the system satisfies the requirement. So for system here, I represented a server with several clients, and requirements are often written in natural language. So this is why you can see this image here. And to address this problem, the approach of model checking is to represent both the system and the requirement into mathematical formalisms. So the system will be represented by a model. So I'm not sure you can see my pointer, but on the left-hand side, you can see a model which looks like a composition of several graphs. And you can think of it as each graph represents the behavior of one client. And you would have another graph representing the behavior of the server, and their composition represents the behavior of the whole system. On the right-hand side, you can see something that might look a bit obscure for now, which looks like a formula. And starting with the letters A, G. This formula here expresses the fact that two processes cannot be in their critical section simultaneously. What I wanted to show on this slide is that we use logical formalisms to describe the property, and to represent the requirement, and we call each formula a property. Okay, so this is just the formalization of in a mathematical world of the system behavior and the requirement. And now the objective of model checking is to come up with a model checking algorithm that takes as input a model and a property and answers yes if the model satisfies the property, or no if it doesn't. Moreover, if it doesn't, most often the model checking algorithm will return what we call a counterexample, which means an explanation why the model does not satisfy the property. So this approach of model checking is generic. So why generic? Because the objective is to have a single model checking algorithm for a whole class of models and properties. And it has been in the past successfully applied to both our hardware and software verification in a variety of domains, of application domains. And I listed a few of them here, ranging from embedding softwares and to telecommunications and planning and so on. So these are, in my opinion, the advantages of model checking. The drawbacks are, in contrast, that the problem itself is undecidable in general, and it is hardly scalable to real-life case study. So we will see more about this in the sequel. The approach of model checking has been acknowledged by, or its importance has been acknowledged by 2 Turing Awards, one to Pnueli in 1986 and one to Clark, Emerson, and Tsifakis in 2007. And in particular, the one to Clark, Emerson, and Tsifakis recognized the fact that model checking had been turned into a highly effective verification technology and applied to industrial case studies. So this was sort of the introduction to model checking. As I said, it has been applied to verify both hardware and software. And in the sequel, I will give very, very simple examples of hardware and software model checking. So the first basic example I start with is a circuit where you have one input value x, one output value y, and a register r. And the value of the output is given by the control function lambda y, and which basically takes the negation of the XOR between x and r, the value of x and the value of r. The register evaluation is given by the function delta r, which takes the OR of the value of x and the previous value of r. So I hope the semantics is clear. And now I'll explain how model checking will approach the verification of such a circuit, very basic circuit. So what we can come up with is a model, so a formal representation, an automaton model, in which the states contain the value of the variable and the register. So each state here you can see on the top left a state where the value of x is 0, the value of the register is also 0. Okay, and with colors I represented the fact that the leftmost and top state in this, top left state, the value of y is 1, represented by the orange color, whereas in the other states, in the 3 other states, the value of y is 0, and that's why they're white. On the edges, you can see the next value of the x signal, so either 0 or 1, and you can see how to evolve from one state to the other depending on the next value of the input signal. So this automaton represents the behavior of the circuit. So that's the model we consider. And one could be interested in checking a safety property. So a safety property could be when the register value is 1, the output is necessarily 0. So this is a safety property. This is a requirement we want to check. And we will explain how to check it on the model. Well, on the model, it reduces to a very simple reachability question, which asks that no state with register value 1 and output value 1 is reachable. And you can see on the picture that there is no state with r equals 1, and the color is orange. So in that case, the property is satisfied. In other circuits, it could be falsified, and then a counterexample or an explanation why the safety property doesn't hold would be a finite path that reaches an error state. So if the instance is negative, then the model checker, the tool or the model checking algorithm would return a finite path reaching an error state. Okay, so this is, I hope, clear. And a difficulty in this approach is that the automaton we built is exponential in the number of variables. So here you can see that we only have 2 variables, or 3 if we count the output variable. And the automaton is already, quite large for such a simple example. So this is one difficulty. So this was the hardware model checking example, and let's go to a software model checking example, a very basic one again. So I represented the pseudocode of a binary search where we are given a sorted array of size n, and we want to, which contains the value x, and we want to, which may or may not contain the value x, and we want to return -1 if X does appear in the array, or the position, the index where it appears if it appears. Okay, sorry, maybe I said something wrong. So -1 if it does not appear, and the index where it appears if it does. So this is just a simple binary search. And one way to abstract the behavior of this program, this very simple program, is to consider its control flow graph, which you might be familiar with, and which is somehow the relationship between the lines of code. So each node in this control flow graph is one line of code. For instance, you can see at node 3, there's or location 3, there's an if branching, which might lead either to line 4 or to line 5, and this you can see on the control flow graph. So this is a very coarse abstraction of the behavior of the program, because we don't take into account the values and both the value of X and the values appearing in the array. Okay, and here I want to consider a liveness property, which namely is that every execution terminates. So either return the index of the position of X in the array, or -1 if it does not appear. So what I claim here is that we might be able to check that on the control flow graph. And the question we ask on the control flow graph is whether every maximal path reaches the state 7 or 8. So on that particular example, you can see that this is not the case. There are paths that loop forever in what represents the while loop. So on that particular example, we see that the control flow graph model is not sufficient to prove termination. So the termination doesn't hold at the control flow graph level, although if you look carefully at the code, indeed this program terminates. Okay, so to overcome this difficulty, one can consider richer model classes than the one of control flow graph. And in general, to deal with the software model checking, or to model software, to model programs, you can add to the graph or automata structure, you can add various data structures, such as counters that will be interesting to manipulate integers. You can add FIFO queues to represent communication channels between several components, and you can add you can consider push-down automata to be able to model the recursion stacks when you have program calls and program returns. So this would be a way to refine the model of control flow graphs of that particular program, and to be able to prove termination. So one difficulty here that we start to see is that if you build a more expressive model, so for instance by adding counters or by adding stacks, then the verification process, the model checking process, will be more costly. So it will be more costly in terms of complexity, and it can even become undecidable. Okay, so this was the second basic example of model checking. So again, feel free to interrupt if you have a question already. So now I'd like to give a representation of what I think is the model checking community. So in my opinion, it gives a wide spectrum of activities from theory to applications. And this is, I guess, something which we have in common with your community of distributed computing, that you can have very theoretical work and also very applied contributions. And I try to depict on this spectrum, or to position on this spectrum, several activities, or more precise activities of the community. So on one extremity, you can think of decidability and complexity questions. So this would be the most theoretical part, I would say. On the other end, at the other end, you can think of real industrial case studies, which call for very ingenious tricks to be able to really treat large scale case studies. And somewhere in between, you have the implementation into prototype tools and experiments, and you also have how to tune both the model classes and the logics to fit a particular class of programs or of algorithms that you want to model check. Okay, so the main message here is to say that the activities are very varied in our community. My contributions are more on the theoretical side, so on the, say, red, orange, yellow part of this spectrum, but there are much more, it is much more diverse in the community. Okay, so let me now come to the outline of the rest of the talk. So after this short introduction to model checking, I'd like to talk about parameterized verification, which is a subclass of model checking techniques, and how they could be developed to apply to distributed algorithms. And then I want to exemplify this on two frameworks, which apply to threshold-based fault-tolerant algorithms. And one of them is threshold automata, possibly with probabilities, and the other one is predicate abstraction. And afterwards, I'll conclude. Okay, so let's start with a very simple distributed algorithm, namely a mutual exclusion algorithm, the one by Peterson. And here I give it, on the left-hand side, I give its pseudocode for two processes, say P0 and P1. And you can see that each of them, so this is the code, sorry, for process I, and you can see that there is a shared variable X, and there are also variables B0 and B1, one for each process. Okay, so this can be modeled on the right-hand side. So the behavior of process I can be modeled by a simple enough automaton with 3 states. So Ni represent the fact that process I is not willing to access the resource. Wi is the case where the process wants to access the resource, and Ci is the critical section. So to move from one state to the other, there are guards, so constraints on the values. Okay, sorry, I see a typo from Wi to Ci. It should be x equals y. So this is a test. This should be a test rather than an affectation. And but from Ci to Ni, so from critical section to normal non-critical phase, the process I releases the token by setting its value bi to bottom. Okay, so transitions can have guards and also can have can affect a new value to the variables. So this is the modeling phase. This is the representation of the behavior of one process. And correctness of this algorithm can be expressed as a safety property here, namely the fact that the processes are not in their critical section simultaneously. So to be able to automatically check that property, what we do is that we build the product transition system, which is represented bottom left of this slide, and it represents all possible interleavings of the actions of the two processes. So on the top of this figure, you can see 2 states. In each of them, the 2 processes are in their end state, not willing to access the shared resource. And the only difference between those 2 states is the value of shared variable x. So left is x equal 1 and right is x equals 0. And one moves from a configuration of this product transition system to another one by one process taking a step. Okay, so this is the representation of all possible interleavings. And if we want to check correctness, well, what suffices to do is to check that on this product transition system, no state of the form C0, C1, and whatever for the values of the variable is reachable. And well, you can see that on that particular model, this is the case. And one way to do this would be to explore exhaustively the set of all executions and check that no state C0, C1 is reachable. Okay, so this was a very simple example of model checking a distributed algorithm. And let me now come to the limits of standard model checking techniques when we want to apply them, in particular to distributed algorithm. Okay, so generic limitation of model checking techniques, and which is not specific to distributed algorithms, is the problem of state space explosion, which I already mentioned a bit earlier. So here you could see on the mutual exclusion algorithm example that the product transition system is exponential in the number of processes. And we saw previously on the circuit example that it is also exponential in the number of variables. So when we want to exhaustively search this transition system, product transition system, the object is very large, and the tools that we implement, they hardly scale to large number of processes or to real-life examples. So there are partial solutions to this that were developed throughout the years, and I listed here a few of them. So it can be a clever encoding of the state space, as in binary decision diagrams encodings. It can be the use of partial order reduction techniques to avoid exploring executions that differ in the order of the actions they take, but not in the states they reach. It can be to limit oneself to bounded model checking, so just to explore for a bounded number of steps the behavior of the system. And it can also be CGAR approaches. So CGAR stands for counterexample guided abstraction refinement. And I will say a bit more, I hope, in the sequel about these kind of approaches. So these, as I said, are partial solutions to the state space explosion. So in some cases, they are sufficient to be able to model check a class of algorithm in practice. So they are sufficient for the tools to terminate, but sometimes they don't suffice. So this is a very well-known limitation of model checking, the state space explosion problem. And the second one is more specific to distributed algorithms. So what we've seen on Peterson's mutual exclusion example is that we had to fix the number of processes in order to be able to build the transition system. So in that example, we fixed the number of processes to be 2, but you could imagine that we can fix it to a fixed number, say 3 or 10. And each time it will give another transition system, and this transition system again will be exponential in the number of processes. And okay, and so the models have a fixed number of processes. Typically, if one uses the model checker Prism, which is a model checker for probabilistic systems, randomized consensus can be proved correct. So some randomized consensus algorithms can be proved correct for 10 participants, but beyond that number, the model is too large and the tool does not terminate. So this is, in my opinion, a real problem when you want to prove the correctness of distributed algorithms, because this property of correctness should hold for any number of processes and not for a fixed value, even if it's a large value. And okay, you can also acknowledge that 10 is not even a large value. So this is the reason, this second limitation, the fact that models have fixed number of processes and we want to verify correctness for arbitrary number of processes, this motivates the introduction of parameterized verification. So parameterized verification can be seen as going to infinity and maybe even beyond. So what we want to move from or to progress from is the fixed instance. So on the left-hand side, you can see those 8 clients and a single server, to an arbitrary number of clients represented by those dots. So you want to be able to check correctness for every number of clients. So you want to prove the property phi, which here represent correctness, for all systems that are composed of n clients and a server. So more generally, the parameterized verification addresses not only the variation on the number of participants, but also you can think of it as all possible network topologies, or all possible failures type, or all what we call more generally parameter evaluations. So this is quite hard because somehow what you want to do is to model check infinitely many instances at once. So you want to check the instance where you have one client, two clients, three clients, and so on. And you want to do this in a single step. So this is the challenge. And a good surprise is that sometimes it is easier in terms of complexity to prove correctness for all n, so for all number of processes, than for a large value of n. So that's surprising, but that's a good news. So again, the objective of parameterized verification is to check correctness for every number of clients or every number of processes taking part into a distributed algorithm. And the whole objective when applied to distributed algorithm is we start with, our objective is to be able to start from the algorithm pseudocode. And here I gave an example that I will detail a bit later. And requirements on this algorithm. So for instance, here it's a randomized consensus algorithm where we want to verify two safety property, namely validity and agreement. And we also want to check one liveness property, which is in that case almost sure termination. So termination with probability 1. So we start from this, and our objective is to come up with a model. So a mathematical representation of the behavior of the algorithm. So this is this automaton-like thingy that you can see on the right-hand side. And so this represents, again, the algorithm. And we want to come up with formulas, and here I listed 3 of them, that represent the requirements, that represent the properties we want to check. So this is one thing. This is the modeling challenge or the modeling task. But most importantly, maybe what we want to come up with are model checking algorithms. So that would take as input a model and a formula and answer yes if the model satisfies the formula and no if it doesn't. So this is the model checking algorithm. And we also want to come up with prototype implementations, implementing those model checking algorithms to be able to test them on benchmarks, so on distributed algorithms from the literature, and check whether the tool does terminate and can prove the requirements that we wanted to on the consensus algorithm we started with. Okay, so that's our general approach. So that's our general goal, let's say. Now you can see that, one important point is that depending, maybe this comes next, depending on the type of distributed algorithms we consider, we will have different models, and depending also on the type of distributed algorithms, we will have different properties. So there is a whole variety of settings to explore, depending on the timing model that you consider, ranging from synchronous to asynchronous, depending also on the communication paradigm, so how processes communicate together, on the failure model, and of course on the problem you address, whether you want to solve consensus or leader election or database consistency and so on. So there is really thousands of settings to explore. And so to me, it really looks like this. It looks like to me is a fantastic playground for model checking, because for each setting we want to design a model class and a set of formulas for which we want to design a model checking algorithm. And so there are really lots of settings to explore, which is great. And in my opinion, it also raises both theoretical and practical issues, and that's also what we are interested in. Okay, I hope this is clear so far. So now I'll explain, I'll go through two frameworks that we've been working on to be able to model check, or to model check threshold-based fault-tolerant algorithms. Okay, so the first one is the one of threshold automata. And I'll try to explain how to model some fault-tolerant threshold-based distributed algorithms into that setting. And I'll give also some intuitions on how to check those automata afterwards. So threshold automata were introduced by Konoff, Veit, and Wieder in 2015, and they've been then extended together with Lazic a few years later. The idea is, as in the control flow graph, to represent control points of the algorithm as location, so as states of the automaton. I'll give an example later. And to use shared variables to count the sent messages of each type. And the transition in this automaton will bear some constraints, some guards, that are linear constraints on the variables and the parameters. Okay, so let me exemplify this here. So this is an example of a threshold automaton where you can see a number of locations, a number of states. I don't know how many, but quite a few of them, maybe 10 states. And what can I say? Okay, on one transition here, you can see the label x1++, and so which means incrementing variable x1, and this represents the fact that the message x1 has been broadcast to all other processes. And we represent this in threshold automata by incrementing a shared variable, which is x1. Okay, and on another transition, going from the left part to the right part, you can see a guard here. So the guard says that if x1 is greater than some threshold, so n plus t divided by 2 minus f, then what we do is that we can move from left to right, and we can increment the variable y1. And so the guard expresses that if x1 was received from at least n plus t over 2 correct processes, then we can send y1, message y1 to all. We can broadcast message y1. So here you might see the minus f factor, which takes into account the possible faulty processes. So in order to check that x1 was received from at least n plus t over 2 distinct correct processes, then we have this minus f factor. Okay. So I hope the model is clear. So we have states, we have updates of shared variables, increments in that case only, and we can have guards on the value of shared variables. And those guards, they include the value of the variables and the value of the parameters. So in that particular case, n, the number of processes, t, the upper bound on the number of faulty processes, and f, the actual number of faulty processes. Okay, so in order to model, first step before model checking those automata is to give them formal semantics, so to give them an operational semantics, and in that particular case, it would be an infinite counter system. So here you want to have one counter per location, so per state of the threshold automaton, and the value of those counter is not bounded because of the parameters. So the value of those counters can grow arbitrarily high because the number of processes itself is not bounded. It's a parameter. n. So we have an infinite counter system, and you can think of it as the counter represents the number of processes that are in a given state or in a given location. So for instance, in that example, k of I1 of initial state I1 is 1, represented by a single token in that state, and k of the counter of E1 is 2, represented by 2 tokens here in that state. Maybe something that I should have made clear earlier is that the threshold automaton represents the behavior of one process, and then we will want to check the interleaved behavior of a composition of several such processes. And with those tokens, we represent the position of each process when executing this threshold automaton. So here we are at a snapshot where there are four processes. One of them is in state I1, one of them is in state D1, and 2 are in state E1. Okay, so we count how many correct processes are in each state, and here the locations D0, D1 represent positions. It's a consensus algorithm, and they represent positions where processes have decided, and D1 typically represents that the process has decided value 1. Okay, so we have an infinite counter system, finitely many counters, one for each location, but the values of these counters can grow unboundedly. And so this is how we model the algorithm, and now let's see how we can specify the correctness property and how we can model check them. So to specify them, we use linear-time temporal logic, so a particular variant of it. I will not go into details, but the important thing is that the atomic propositions that we use in that logic check whether a counter value is 0 or not. So check whether some process is in that location or no process is in that location. And using those atomic propositions, using those predicates, we can express agreement as a safety property. So agreement states that no two correct processes decide differently, and this can be expressed as this logical formula. So if you know a bit about LTL, linear-time temporal logic, then this reads as, okay, if left-hand side says at some point one process decided value V, so the counter for dV is positive, this implies that forever, this is the G operator, no process decided value 1 minus D, so the counter associated with location D 1 minus D is 0. Okay, so this is how to express agreement. And we can also express termination, which is a liveness property, as we've seen earlier. And liveness here would be expressed as eventually, so the F operator, all locations that do not correspond to a deciding location, they are empty. So all counters for non-D location are 0. So, okay, so this is the modeling part for the requirements. We use, again, a linear-time temporal logic fragment. And yeah, the basic elements in that logical formulas are whether a counter value is 0 or not. Okay, and the very important result is that if you're given a threshold automaton and a specification in that logic, and also a resilience condition that links, that gives a relationship between the 3 parameters N, T, and F, one can decide whether for all parameters that satisfy the resilience condition, the system we obtain satisfies the property. Okay, so this means that the model checking problem for threshold automata and specifications in this fragment of logic is decidable. So it is decidable, and it has been implemented into a tool, which is a ByMC for Byzantine model checker, and which is available online and that you can test if you want. Okay, So this brings me to the second question, is namely, when you consider consensus algorithms in the presence of failures, very naturally, to overcome the impossibility result by Fisher, Lynch, and Peterson, researchers came up with randomized solutions to be able to break the symmetry between the processes. So one such solution has been proposed by Bertrand, and this is the pseudocode of his algorithm is depicted here. So this is of course the pseudocode for a single process, for each process. So each process has an input value, either 0 or 1, and the algorithm proceeds in rounds. It is completely asynchronous, but it proceeds in rounds. And in each round, the processes will broadcast and receive messages. And if at some point they receive enough support for a value, then they will update their estimate. If there is a strong majority on that value, they will decide that value. But if the situation is unclear, they will toss a coin, and depending on the value of the coin toss, they will update their new value for the next round. So this is the orange update. V is updated to a random value, either 0 or 1, and then we proceed to the next round. So when we want to handle such algorithms, the threshold automaton setting cannot do it immediately, and there are at least two modeling challenges. So one of them is that here we need to be able to represent unboundedly many rounds, so rounds and possibly in an unbounded number. And we also need to be able to represent probabilistic choices. In that case for local coin tosses, but it could also be for global ones. So in order to address this, what we did was to propose probabilistic threshold automata, so a probabilistic variant of threshold automata. And so it resembles the threshold automaton you've seen before, and there are two differences. So one of them is that you have probabilistic choices, where you can see here that one moves either to CT0 or CT1, each of them with probability half. And also we represent the round switch, so the switching from round K or R, to round R plus 1 with those dashed arrows going back to the initial state. And this represents the fact that there can be several rounds that proceed sequentially. Okay, so this was for the modeling thing, and then we had to express the correctness property. So we had to express agreement, validity, and almost sure termination. And here you might be able to see differences to the previous setting of normal threshold automata without randomization. Namely, the specifications we have here, they talk about multiple rounds. So you can see that agreement, for instance, says that no two processes decide differently, even if they are in different rounds. So this is why we have quantifications over two round numbers k and k prime. Okay, so the specifications are over multiple rounds, and we also have probability guarantees. So for instance, termination here is only ensured with probability 1, so we need to be able to express the fact that the probability is 1 under all adversaries to terminate. So this really raises or increasing the difficulty of checking such properties. So I will not give all details on this, but what we managed to do was to verify correctness, so both the safety and the liveness properties. And safety was much easier, and it's often the case. It's often it's a general lesson in model checking that checking safety is easier than checking liveness. So here, safety has to hold on all executions, and this implies that the probabilistic choices can be transformed into non-determinism, and so the probability values do not really matter, and it really helps. Also, we used communication closure to be able to reduce to a single single round threshold automaton, so without the back dashed arrows, by reordering the actions. And the last element we used was to exhibit round switch invariance to be able to reduce the specifications to also to single round specification. So somehow our objective was to be back to the normal setting, a threshold automata with a single round, and also, of course, the specification speaks about this single round threshold automaton. So this was for safety. For liveness, it was harder because it has to hold on almost all executions, and here the probability values do matter. So what we succeeded to do was to prove almost short termination for a restricted class of adversary, which we called round rigid. And also something, a limitation is that we only provided sufficient conditions for almost short termination. And we did not provide necessary and sufficient conditions. So these are two limitations, in my opinion, of this first work we did. So first of all, we provided sufficient conditions only. So which means that if we manage to prove those conditions on the model, then we know it ensures correctness of the algorithm. But if we don't manage to prove it, we don't know whether it is because of this somehow abstraction. And another drawback, in my opinion, of this approach is that it really mimics the manual proof. So we follow each step of the manual proof, and somehow, in my opinion, it is a difficulty to be able to generalize the approach to other types of randomized distributed algorithms. Okay, so okay, just to finish with this approach, we implemented it and tested it, and tested it on several classical randomized distributed algorithms from the literature. And you can see that for most of them, the verification time is very slow. Is very low. Is very good. So that's yeah, that's good news. Okay, so I'd like to maybe take 5 minutes to talk about another approach which tries to overcome the shortcomings I highlighted of the threshold automaton approach. I'll try to, I see that there is not much time left, so I will be a bit faster on this. I'll try to convey the main message. Okay, so this second approach, I'll illustrate it on a variant of phase-king algorithm. So for simplicity, this is not, if you look carefully, this is not the pseudocode of the real phase-king algorithm. It was just so that it fits better on the slide, and especially the model also fits better. Okay, so again, it's a consensus algorithm. It is structured somehow in layers. So here rounds, but it could be finer grain. And without loss of generality, we assume that the processes send their local state as message contents. Okay, the number of rounds is unbounded. Well, in fact, it is related to the number of faults, of faulty processes. So there are t+1 rounds if t is the number of faulty processes. And this particular algorithm is synchronous, but we can also deal with that technique with the asynchronous algorithms. So the idea is to represent the algorithm as a layered threshold automaton. So here you can see the layers 0, 1, 2, and so on. And the same pattern repeats over time. So from 0 to 1, 1 to 2, and so on. It's exactly the same pattern. So here, in fact, it's a complete graph. And I could not draw on each edge the guard because there are too many edges. So I only gave on the right-hand side an example of guard. So when you move from V1 of layer L to V0 of layer L+1, the guard would be the following. So, okay, what does it mean to move from V1 to V0? It means to change one's value from one's estimate from 1 to 0. What I did not explain yet is that at each layer there are 4 possible states. V0 and V1 represent whether the current estimate is 0 or 1, and K0 and K1 represent, so K0 represent the fact that the process is king, and its current estimate is 0, or the process is king, K1, and its current estimate is 1. Okay. So here I only gave an example of a guard to update one's estimate into V0, and so there are two possibilities: either either the number of processes with estimate 0 exceeds large majority n over 2 plus t, or the number of processes with estimate 1 does not exceed this threshold, and the process is the and the king process at value 0. Okay, so these are conditions for one process to update its value to 0 in the next round. Okay, so the important thing is that we have threshold automata, but layered in structured in layers, and the layers really repeat themselves. Okay, now I need to skip some details, but the semantics of this model could be given as a full configuration. So full configuration gives the sequence of states each process goes through during the execution, but also the set of messages they received at each layer. So for instance, here you can see that P0 has received from itself, P0, but also from P1 it has received the first two messages, and from P2 it has received the first two messages, V1 and V0. Okay, and by successive abstractions, we can represent such a full configuration into what we call a guard configuration, where, so that's more quite important. You have a series of constraints. So for instance, V0 positive, K0 positive, and so on. So these are what we call predicates. And at each step, we look which predicate holds, represented by T, and which doesn't hold. And okay, so this gives the execution, the valuation of those predicates over the execution. And starting from this guard configuration, we are interested into constructing an automaton that will represent the possible executions of the distributed algorithm. So what we do is that we view each of those evaluation of predicates as a letter over a huge alphabet, okay? And each such letter will be a state in the guard automaton. So you can see gamma 0 to gamma 4 as states of the guard automaton. And because on the left-hand side there is an execution, this means that there is a transition from gamma 0 to gamma 1, and also from gamma 1 to gamma 2, and so on. But the guard automaton, of course, can be larger, so there are more states, for instance, the delta here, and there are also more transitions. The important thing is that we can, using an SMT solver, one can decide whether there is a transition from one state to the other. So we check the existence of a transition thanks to an SMT solver. And the interesting property that we have here is that the language of the guard automaton is another over-approximation of the set of all executions of the layered threshold automaton. Okay, so we managed to over-approximate the behavior of the layered threshold automaton. So the method is incomplete because we might add new behaviors by building this guard automaton. Yet it's interesting, we think, because it is sufficient to, for instance, prove correctness of the phase king algorithm. Okay, and in my opinion, a very interesting thing is that the analysis can be refined by adding more predicates. So the guard automaton that you can see top right of this slide was constructed for a fixed set of 9 predicates that you can see on the top left. But if you add more constraints, then this would refine the guard automaton. Okay. So somewhere here on that slide, which I'll skip, I think, I wanted to compare the two approaches I briefly presented. the one with threshold automaton and the one with the guard automaton. So the two approaches. Okay, let's not go into those details, and I'll jump to the conclusion to leave a few minutes for questions if you have some. Okay, so today I wanted to explain what, in my opinion, parameterized verification and more generally model checking can bring to the distributed algorithms community. So when we develop parameterized verification techniques, they can be applied to so far simple and standard distributed algorithms. So very simple, as you could see. What we did so far was to check basic consensus algorithms. And I realized that these are algorithms that date back the 80s or so. So we are far from model checking automatically current distributed algorithms. A real advantage is that it provides automated correctness proof. So in my opinion, that's good because it alleviates the manual proofs that can be error prone, or sorry, the drawbacks of manual proofs because they can be error prone. And also it's, in my opinion, better than a simulation, which would not be exhaustive. And an important thing is that parameterized verification as general model checking techniques, they are generic. So what we provide is a model checking algorithm for a class of distributed algorithms, not for a single algorithm. So if you want to change a bit the thresholds that you have in your algorithm, or if you want to change a condition in an if branch, if branching, then you don't need to redo the analysis. Well, you need to rerun your model checking tool or model checking algorithm, but this model checking algorithm is common to the whole class of distributed algorithms. And this, I think, can be good if you want to adjust or to tune the distributed algorithm you are designing. Okay, there are more frameworks than the one I presented today. So by a number of researchers from the model checking community, I only listed a few there. And I'd like to conclude, sorry, and that to the best of my knowledge, there are two available tools that you can try out. One of them I mentioned is ByMC for Byzantine Model Checker, and the other one is Peregrine, which is related to the verification of population protocols. So the last line just above. Okay, and okay, so I think there are still many challenges for our community to be able to prove correctness automatically of distributed algorithms. So my current interests are twofold. So first one is to try to design a compositional analysis of threshold automata to improve scalability. I can give more details about this. And another thing is to consider another type of consensus algorithm that is more based on shared memory, as the one by Asmus in 2002. And I also list more mid-term and long-term objectives. I think an important thing would be to be able to automatically extract models from pseudocode. Because so far what we do is to look at the pseudocode and turn it into an automaton. And so here there is some, there can be some errors. Something very challenging and quite interesting would be to be able to perform a quantitative analysis of randomized consensus algorithms. So far what we did was to check whether a probability is 1, but we could not compute whether a probability is 0.9 or compare a probability to a threshold bound. Something also more long-term is to be able to automatically synthesize complexity measures of some distributed algorithm, for instance, the convergence time. And I guess the graal or the very, very long-term objective would be to be able to automatically synthesize correct by design distributed algorithms. Okay, so that's it for me. Thanks a lot for your attention. I'm looking forward for questions if you have.